I've begun recording now. So we've got House Algebros up first. So you guys have the floor. Please go ahead. Okay, so maybe what we can do, I'm sorry, maybe you're going to be presenting, again, whoever's going to be presenting of you three in the classroom, just sit right there in this chair here in front, so you're closest to the microphone, and whatever you say can be recorded. Can everybody hear? Can you over at home? Can you hear? I switched microphones to the microphone in the classroom. Can you hear? And can you hear Daniel?
No, teacher.
No, and when we hear you, it sounds with an echo. We can hear you with an echo.
With an echo. Give me a moment. Okay, Daniel, can you speak, please?
Hello.
No, we can.
We can hear him now.
Okay, good.
Yes. So presenting exponential and logarithmic functions. So to start off, we're going to talk about Leonhard Euler and a bit about his life. He was born on April 15 of 1707 in Basel, Switzerland, and he died on September 18 of 1783 in St. Petersburg, Russia. He was a mathematician and physicist and was one of the founders of pure mathematics. He made decisive and formative contributions to subjects of geometry, calculus, mechanics, and number theory. He developed methods for solving problems in observational astronomy and demonstrated useful applications of mathematics in technology and public affairs. His math abilities earned him the esteem of Johann Bernoulli, and in 1727, he moved to St. Petersburg, where he became an associate of St. Petersburg Academy of Sciences. And on 1733, he succeeded Johann Bernoulli's son, Daniel Bernoulli, to the chair of mathematicians. And he carried integral calculus to a higher degree of perfection. He developed the theory of trigonometric and logarithmic functions, reduced analytical operations to a greater simplicity. In 1741, he became a member of the Berlin Academy, and in 1748, he developed the concept of function in mathematical analysis. After Frederick the Great became less cordial towards him, Euler, in 1766, accepted an invitation of Catherine II to return to Russia. Throughout his life, he was absorbed by problems dealing with the theory of numbers, and in this, he found his greatest discovery. And in 1783, he discovered the law of the quadratic reciprocity. And in St. Petersburg, on the 18th of September of 1783, after a lunch with his family, he was discussing with Lexel the newly discovered planet Uranus and its orbits, and he just collapsed and he died from a brain hemorrhage. And that was a bit of his life. So now we're going to talk about his number. So the number E is often called a natural number or Euler's number. It is an important mathematical constant. It's like talking about P. It's a constant, and it's approximately equal to 2.71828. And it's used as the base for a logarithm. The corresponding logarithm is called a natural logarithm, and is written as ln x. And just a side note, the natural logarithm of E is 1, and the natural logarithm of 1 is 0. There are several different definitions to this number, and most of them are from calculus. And one of them is that there's a limit to the sequence of, in general terms, and there's a formula to that is 1 plus 1 over n to the n. And another one is that e is the unique number that when you want the area under the curve of y equals 1 over x, that from 1 to e, under the curve, that's 1 square unit. And another definition that involves that number is the infinite series, which is 1 plus 1 over 1 to 1 plus, well, that's just 1. But in the second is 1 over 1 plus 2, then 1 over 1 plus 2 plus 3, and so on. And it can be shown the sum of the series of e. So yeah, that's it. And here is the example I was talking about. So we have the graph of the equation y equals 1 over x. So you can see that from 1 to e, which is 2.70 something, the area of the shaded part, it's equal to 1 unit. So that's why it is very important.
Okay, then we're going to talk about what is an exponential.
While Arturo sits down, this is just a cultural comment that isn't really important. It's just have it on radar. Actually, it's not pronounced Euler. It's pronounced Euler.
Euler.
Yeah, that's because the name it's European. I'm not sure if it's German or Swiss German or what's the origin, but the letters EU in German or in Swiss German are pronounced Euler. So it's not Euler's number, it's Euler's number. Obviously, over here in America and Mexico, we don't pronounce it as Euler. The most common is we say número de Euler, or even in English, we say Euler's number. But the correct pronunciation is Euler. Euler's number. Okay, try to speak loud so we can catch you.
Okay. So what is an exponential function? An exponential functions have the form of f of x and b of x, where b is greater than 0 and b can never equal to 1. A good example of exponential function is the growth of a bacterium. Some bacteria double every hour. So if you start with one bacterium and it doubles every hour, you will have 2 of x bacteria after x hours. And it can be written as f of x equals 2x. And here's an example of the exponential functions in a graph. What does a mean in an exponential function? An exponential function is a function, is a mathematical function in the form of f of x equals ax, where x is a variable and a is a constant, which is called the base of the function, and it should be greater than 0. And here an example we can see on the right is where we can find the range of this one, which is always going to be all real positive numbers. The range can never be negative. And the domain is all real numbers. What does e mean in an exponential function? The letter e is used in many mathematical calculations to stand for a particular number known as the exponential constant. The exponential constant is an important mathematical constant and is given the symbol e. Its value is approximately 2.718, yada, yada, yada. And here's another example of an exponential function, where the range is always going to be all real numbers, and the domain, and the range is going to be all real numbers always greater than 0, never negative.
So now after exponential function, we have the logarithmic functions with the same base a and base e. So what are logarithmic functions? Logarithmic functions are the inverses of the exponential functions. The inverse of the exponential function y equals ax is x equals ay. The logarithmic function y equals log ax is defined to be equivalent to the exponential equation of x equals ay. Y equals log ax is only under the following conditions of x equals ay or a less than 0 and equals 1. It is called the logarithmic function with base a. So base a is a given number x and a base a to what power y must a be raised to an equal of x. This unknown exponent y equals a log ax. So you see a logarithmic is nothing more than an exponent. By definition, a log x equals x for every real x less than 0. And I put we put an example here, and we notice that the domain only consists of positive real numbers, because the domain in a logarithmic function, all the real numbers are greater to 0. And the range also is only real numbers. So base e is the logarithmic function that is also called the natural logarithm. This is much like Daniel said when he was talking about Euler, and that, well, it's his number. It is denoted by ln x, and the natural logarithmic function is y equals ln x. And in this graph, the natural logarithmic function y is equals ln x, and it's shown in the graph.
Okay, so here we have some easy examples about exponential equations and logarithmic form. So first, here the picture that's beside the examples title, it's like a rule. The one in the left is the exponential form of a function, and the one on the right is the logarithmic form. So in the first 3 examples, to solve, we have to convert the exponential equation to the logarithmic form. So it's really easy. We just have to change the order. For example, in the first one, we have 3 elevated to the exponent of x, and that's equals 7. So the only thing we have to do is change the order, like the picture here tells us. So the answer would be x equals to log with the exponent 3 and between parentheses 7. And it's the same with the other 2 examples. The only thing that changes is that the exponents are a little bit more complex. On the second part of the examples, it's different. We have to do it backwards. The problem gives us a logarithmic equation, and we have to convert it to the exponential form and then solve for x. So first we change it, and it gives us 7 elevated to the exponent of x equals 343. So since 7 elevated by the exponent of 3 gives us 343, the solution would be that x equals 3. Now, if we talk about the applications of this topic in real life, there are various real life applications that can be modeled using exponential and logarithmic functions. Remember that while applications are drawn from many different disciplines, the mathematics remains essentially the same. So here we have the applications for exponential functions. We have population growth, compound interest, and isotope half-life. And for logarithmic functions, we have hydrogen ion concentration, that's basically about the pH scale, the earthquake intensity, that's about the Richter scale, and sound intensity, that's about the decibel scale. Now we're gonna talk a little bit more about 2 examples of application. The first one is population growth. And this data, such as population, can be modeled using exponential growth decay. The general formula to calculate this type of things, it's this formula. That's the total value, equals to the initial value times the factor of growth decay elevated to the exponent of t, that is the number of time periods. And then on this one, that's the hydrogen ion concentration. The pH scale measures a substance acidity or alkalinity by giving it a pH value of 0 to 14. The concentration of hydrogen ions in a substance is directly related to its pH value. And here we have the formula for this, and you might recognize it a little bit because in chemistry, we are actually seeing something similar to this, we're using logarithmic equations. So here we have an example of a situation in real life where we would use logarithmic equations. So the problem says that Peter inherits $10,000 invested in a guaranteed investment certificate at 6%. How long will it take to be worth 15,000 if it's compounded monthly? So here are 3 examples of formulas that are usually used in this type of situation. The first one is for compound interest. That is the one that we'll be using for this problem. Then we have the one of discrete growth and continuous growth. So the first step for this, for solving this problem, will be choosing our formula. That's this one, the one about compound interests. And we have to substitute in this formula. So for A, that stands for the final amount, that is 15,000. And then that equals to P, that's the principal, that's the amount that we invested, that Peter invested, that's at 10,000. And then between parentheses, we have 1 plus R, that's the rate, that's 6%, but because it's percentage, we write it with decimal point, and that's 0.06 divided by N, that's the number of months, that will be 12 because we're talking about a monthly compound. And then that's elevated to the exponent of N times T, and we already established that it's 12. And T is the variable that we're looking for, that it's how much time will it take to make it 15,000. So then we substituted, now we just solve for T. So first, we will divide each side by 10,000 to remove this multiplication right here. And that will result in 1.5 equals to 1.005 elevated by 12t. And then here is where we use our exponential and logarithmic knowledge. We will apply log to both sides. And if you remember on the previous examples that we saw, the picture beside the examples title, there we have a way of changing the order here. So that's what we do. The exponent, we can write it before we write the log. So then we just divide each side by 12 log in parentheses 1.005, so we can solve for t and leave it alone. And that's going to give us 6.77 years. And that's the answer to our problem. And that's it for our presentation. I don't know if anyone has any questions.
Okay, thank you, you guys. Fernanda, Daniel, Alfredo, and Arturo. Good job. Good job, you guys. Particularly good job in the last part where you're talking about the applications. Good job. Good job. Let's stop sharing the screen for a moment. I'm just going to make a few like takeaway comments in each presentation. So Euler was an important mathematician. I think the concepts of Euler are very important because we see his contributions in a lot of things today. It's really unfortunate. I don't know if you guys noticed when you guys were researching the
biographies of these people, Euler, Kramer, any of these famous mathematicians or physicists. Like, I mean, they were famous people in their times, but usually they died in a really nasty way. So they either just dropped down, they either were poor, I mean, it's really tragic in most of the cases. Daniel?
I forgot to mention, he first lost sight in one eye, on the other eye, and that was a big problem for him because he had a lot of math and he said that he wasn't able to write it down. So like a lot of his, like maybe more of his discoveries would have been known. Was able to write them down.
Yeah, and a lot of these people, they obviously the healthcare in those times isn't what we have now. So a lot of them died and in very tragic ways, and a lot of them died penniless, without any money. So, but Euler gave us a bunch of things, but one of the things he gave us is Euler's number. Now, it's interesting, and not to get too dramatic here, but math and physics and nature and everything that exists in the universe is really a perfect system. It's very, very interesting because you've got numbers like Euler's number, like pi. There are these very weird numbers that represent or help us, I'm sorry, understand things that happen in real life or behaviors in real life. So one thing, I teach a class, this is not a class I teach to the global program students, to other students, it's a control systems class. And one of the first things we see when we're talking about control systems is it would be really cool if things around us behaved linearly. So linearly, we talk about linear functions. So it'd be really cool if everything behaved linearly, right? But the reality is that things around us do not behave linearly. They behave usually with exponential and logarithmic behaviors. And those are the things that you guys were talking about and Fernando was touching upon at the end. For example, the Richter scale. We know about the Richter scale because we live in earthquake country. But you do know that an 8-point magnitude earthquake is not 2 times larger than a 4-point earthquake. The Richter scale isn't linear. So you can feel a 4 earthquake and you're like, oh, something moved. And you're like, well, an 8 earthquake, it means that it moved 2 times more stronger. We've all been in a 4-point earthquake magnitude, right? It happens frequently in Mexicali. I don't know how many of you remember the close to 8-point earthquake that we had in Mexicali a few years ago. It's not double the amount. It's logarithmic. The behavior of populations and bacteria, and we know this for what happens in the pandemic. So one person gets infected, then another person gets infected, but that person has contact with 2 people, so now there's 4 people infected. Some of these have contact with another, one had contact with 2 people, another had contact with 3 people, another had contact with 5 people. Now suddenly there's more than 10 people infected. They had contact with other people, now it's 100 people infected. It's not linear, okay? It's exponential. It starts growing really quickly. So exponential and logarithmic functions are very interesting because they represent behavior in real life. The last example that Fernando was showing is very interesting. And I'll just leave this as mental gum for you guys. Learn about finance. Learn about finances, at least for your personal finances. Okay. The example that Fernando gave is, okay, I inherited $10,000 and I'm going to put it in the bank with 6% compounded interest. How many years has to go by before I have $15,000? And that's because I'm depositing $10,000 and compound interest means after a year, it's going to be $10,000 and 6% of $10,000. But the next year, it's going to be $10,000 plus 6% of $10,000 plus that 6%. And so the interest is adding towards the amount, and it's going to be growing in with the behavior that was shown there. That's an interesting example because I'm gaining money, right? It happens the other way around with credit cards. Be very careful. So I spent 1,000 pesos this month, and I only paid the minimum of the credit card, and the credit card taxes me, I don't know, 6% each month. And so I'm only paying the minimum. And that means if the minimum was 200, I only have to pay 800 next month. Well, yeah, it's 800 plus the interest, and plus the interest, plus the interest, plus the interest. So the same case where you had 10,000, now you have 15,000. If you turn it the other way around and it's money you owe, you can get into debt really, really quickly. So that's also represented with exponential and logarithmic functions. And I'm glad, I'm glad you guys mentioned that you're seeing some of this in chemistry, because there are a lot of biological systems that have these behaviors. Good job. Good job, you guys. Okay, so I'm sorry, good job with team algebras. Alfredo, you wanted to say something. Go ahead, please.
Yes, about the
Sorry.
can you explain again about the earthquakes that is not linear?
Yeah, it's so I'm not an expert on the Richter scale, but it's not linear. The way they measure the earthquakes has to do with the amount of vibration you have and how strong that is. But it's not linear. And again, I'm not an expert on the Richter scale. I only know what I can tell you or transmit you right now. You've felt earthquakes, right, Alfredo?
Yes.
Yeah. So try to remember when you're in your house and suddenly something starts moving, like, oh, it's an earthquake. And then you go and you check, and how strong was that earthquake? Normally the slight tremors, right, are around 4 or 5, right? The ones we kind of feel that are not very strong, but we kind of feel them, right? Do you remember the 7-point, close to 8-point earthquake that we had here in Mexicali?
Yes, in 2010.
2010. That earthquake wasn't 2 times larger than when you felt the 4. It was much larger. So the Richter scale isn't linear. So I felt a 3.0 earthquake. Oh, it felt like this. Now it was a 6.0 earthquake. Oh, it's 2 times larger than the 3. No, it has a logarithmic behavior, and that means that when we increase the scale, it's going to be increasing at a larger rate. So that's why if we have a 4.0 earthquake, it's probably not going to be very complicated. But if we have an 8.0 earthquake or a 9.0 earthquake, that's going to be really, really damaging. Okay. Another example I can give you, Alfredo. We all know sound. Have you heard the term decibels? So the sound is decibels, but sound travels through a medium. So if you're very close to a speaker, you're going to hear things very loud because it's hitting you. But if you're farther away, the sound diminishes. And it doesn't diminish linearly. It diminishes exponentially. Okay. And so that's why sound is measured in decibels. And the decibel scale is a logarithmic scale. It's not a linear scale. So again, if things in real life were linear, man, the mathematics would be really, really easier to do things. But the reality is that all of the phenomenon, or most of the phenomena that are around us, are not linear. And they can usually be represented by exponential or logarithmic behaviors. And that's why it's important to understand. Okay. Good job, you guys, with this. Did I answer the question, Alfredo? Was it relatively clear?
Yes. Thank you.
Thank you, Alfredo. Good job, you guys. I really liked the last part with the examples. That was really good. Let's go with our next team. And I think team number 2 or house number 2 is, I think it's Deathly Signs, if I'm not mistaken. Let me just verify here. I think it's I think house 2 is Deathly Signs. Yes, we've got Deathly Signs, Pi Waves, and then Jokers. And we're going to go long until we finish the presentations, and then we'll leave. So Deathly Signs, go ahead. The floor is yours.
Okay, good morning. We are
I love the fact that you guys used a matrix theme to talk about matrix. That's just, if you didn't do it, I would have made it some sort of comment because it was a no-brainer. Good job. Go ahead.
Well, we're going to present you the topic of Introduction to Matrix, Algebra, and Methods for Solving Equation System, Gauss-Jordan. The main topics we're going to talk is the matrix operation, addition, subtraction, and multiplication of a matrix by a number, linear systems of M equation of M variable matrix representation, the Gauss-Jordan biography, the Gauss-Jordan method for solving a linear equation system, and examples and applications. First, we have to talk about what is a matrix. A matrix is a rectangular array of numbers or expressions arranged in rows and columns. Important applications of matrix can be found in mathematics. Okay, the first operation we're going to talk is about the additions. The addition of a matrix is the basic operation performed to add two or more matrices. Matrix addition is possible only if the order of the given matrix are the same. By order, we mean the number of rows and columns are the same for the matrix. Given two or more matrices of the same order, the result of the sum is another matrix of the same order whose elements are obtained as the sum of the elements placed in the same place of the other matrices. And in the example, we can see that the one and the other one of the matrices are in the same place, so they added two, and the result is the sum of the others. The other one is the subtraction. Matrix subtraction is exactly the same as a matrix addition. All the constraints valid for addition are also valid for matrix subtraction. Matrix subtractions can only be done when the two matrices are the same size. Subtraction cannot be defined for the matrices of different sizes. And mathematically is P minus Q is equal to P plus minus Q. And it's the same procedure as when you make an addition. And then we're going to talk about the multiplication. To multiply any matrix by a real number, all the elements of the matrix are multiplied by the number. As we can see in the example that we are multiplied the matrix by -2, we multiply each number of the matrix, and that is the result.
I'm going to talk about linear systems of M equations of N variables matrix representation. So this is a long title, so I thought it would be the best for it to be explained with different colors to represent the steps of how we can represent the linear system in a matrix. So first we start off with learning what a linear equation consists of. It consists of coefficients, unknown variables, and constants. These variables and coefficients will end up giving us a constant, which we'll be using to understand what the variables are. Then on the right side, we can see a linear system, which is just an array of these linear equations that we are going to be using to being able to find the variables we need. These M equations of N variables are called that because of you see in the equation on the top right, it says AMN. It really doesn't, there's a lot of numbers there, but we are just going to be using this formula for as long as we have. This formula works for a finite amount of numbers, and it doesn't need to be that long, but it works for any kind of linear system. So in order to make the system work into a matrix, we need to separate the coefficients from the variables. So it would be ending up like in the bottom right, where we have the coefficients on the left, the variables in the middle, and the constants on the right. That's how we separate them for us to work with.
Okay, so there are two important names that everyone should be aware of or know of when discussing the Gauss-Jordan system. The first one would be John Carl Frederick Gauss. Gauss was born on April 30 of 1777, and he was the only child of a poor family. He was considered a rare find during his time among mathematicians because of the ability he had to retaining big loads of information and being able to make a number of calculations in his mind without making mistakes most of the time. This set of skills maintained their quality along his lifetime, which just makes all of this a bit more impressive. He studied in the University of Göttingen, where he would later graduate and continue to prove his extraordinary abilities till the day he died in 1855. Gauss is mostly known for the Gaussian elimination, which leads us to the second person we should be aware of. This is Wilhelm Jordan, and he was born on March 1st of 1842 in Ellwangen-Württemberg. This place is a historical German territory that roughly corresponds to the cultural linguistic region of Swabia in Germany. And he was a German geodesist who dedicated most of his time and life's work to surveying Germany and Africa and founding the German Geodesy Journal. Jordan completed his studies at the Polytechnic Institute in Stuttgart, and he's known for the Gauss-Jordan elimination algorithm. What Jordan did with this algorithm is that he decided to improve the stability of the system, and he minimized the squared error in the sum of a series of surveying observations. Next is the appliances of the matrix operation in real life. So contrary to popular belief, matrices are used in our day-to-day life more than we thought. We can find matrices even in our personal computers, such as in Adobe Photoshop. And Adobe makes the use of matrices to process linear transformations in order to render images as well as other things. And in physics related applications, matrices are used to, as the presentation says, to study electrical circuits, quantum mechanics and optics. Also, if we were to talk about something more related to us aspiring engineers, engineers normally use matrices to model physical systems and perform accurate calculations of complex mechanics in order for them to work. In electronics, networks, airplanes, even spacecrafts, and all sorts of stuff like that, all require perfectly calibrated calculations and computations, which are obtained from matrix transformations. And in hospitals, medical imaging, CAT scans, and MRIs, all of this use the matrices to operate.
And now we have the Gauss-Jordan method for solving linear equations. And well, this is called the elimination method. And it is an algorithm that can be used to solve systems of linear equations. It relies upon three elementary row operations. One can use on a matrix, and well, these are the ones. First, we have to swap the positions of two of the rows, or we can also multiply one of the rows by a non-zero scalar, or add or subtract the scalar multiple of one row to another row. And well, to understand this better, here we have some examples. This is, for example, swap the positions of the first and third row. Here we have, this is going to the top and this is coming to the bottom. Then we have multiply the second row by 3. That's another thing that we can do. And well, here we have the result. And we can also add twice the first row to the second row. And here we have it, well, how you can do that. Here we have a really important part of the method, which is the reduced row echelon form. And well, first of all, the elimination's main purpose is to use the elementary row operations on an augmented matrix to reduce it into the reduced row echelon form. And well, in order to do this, it has to have like 4 conditions present. And well, here we have the explanation of it, which is rows with 0 entries are at the matrix bottom. The leading entry of each non-zero row is to the right of the row's leading entry directly above it. The leading entry is isn't any non-zero row is 1. All entries in the column containing the leading entry are zeros. Well, this can be a little bit like hard to understand, but well, by looking at this, this is like once we have the linear equation and we turn it into this, at the end, in order to get the right result, it needs to be all zeros in here, all zeros in here, and the diagonal has to be all ones. It can be negative or any other number. And well, there isn't really like definite steps that you need to follow in order to solve the equations. It's more like you have to do a lot of thinking. And here are some of the things that you can do, like tips in order to do this easier. And first of all, you can swap rows so that all rows with 0 entries are on the bottom of the matrix. Swap rows so that the row with the largest leftmost digit is on the top of the matrix. Multiply the top row by a scalar that converts the top row's leading entry into 1. Add or subtract multiples of the top row to the other rows so that the entries in the column of the top row's leading entry are all zeros. Well, this that I just mentioned is the like the main 3 things that the elimination method does that I mentioned before. And we have to repeat this process for the other numbers. And we can also swap the rows so that the leading entry of each non-zero row is to the right of the leading entry of the row directly above it. And here we have an example. This is the linear equations. And first we have to transform it into this, the augmented matrix of the system. And here we can see that we only grab the coefficient. Here we have 1, the 2, the -6, 3, -4, and 14. Then we need to do the reduced row echelon form. And to do this, the first thing that we're gonna do is to multiply the first row by -1. So it's gonna be 1 here, and it's gonna be -2 here, and 6 here. Then we're gonna multiply the first row by 3 and subtract it from the second row. And here we can see that we have a 1 here, and now we're gonna have a 0 here. We're just missing another 1 here and another 0 here. And to make the second entry of the second row 1, we can multiply the second row by 1/2. And well, it's gonna end up looking like this. And now we're just missing the last 0. Okay, so now what we're gonna do is the second entry of the first row should be 0, like I already mentioned. And in order to do that, we multiply the second row by 2 and add it to the first row. And here we have it like 0 times 2, it's 0, so it's gonna stay the same, the 1. And then here we're gonna have the 0 that we were missing, and this is staying the same. And here we are gonna have a 2. So now that we have the echelon form, well, we transform it into this if it's easier for you to understand it, because this column is the x and this column is the y. So here we have 1x and 0y, so the result is going to be x equals 2. We have 0x here and 1y here equals -2, and that would be the answer for it. And here we have another example, and well, this is a bit different because in the last one we only had 2, and here we're gonna have 3. So we need to remember that this ones need to be 0 all the time, and that this ones have to be all 1, and like here we have a -1, and well, that's not right. Okay, so here the first thing that we're gonna do is row 1 minus row 2. And the only one that's gonna change, as we can see, is this one. Then we're gonna have multiply row 1 times -2 and then add it to row 3. And we're gonna end up with this. We already have 2 zeros here. And then we have row 2 plus row 3 multiplied by 3. And as we can see, this one is the one that's changing. We already have the 3 zeros. We're missing the other 3. We're gonna multiply row 1 times 3, then subtract it from row 2. And here we have the result of it. Then we have row 3 plus row 2. And here we have it. We're just missing this 0 now. And the last thing that we're gonna do for the part of the zeros is multiply row 1 times 2, then subtract it from row 2. And we have all the zeros now. And this is the easiest part in my opinion, because in order to turn this into a ones, we are only going to be multiplying to 1/6, 1/2, and 1/3. So now we have all ones here, all zeros here. And well, since we have the x here, it's gonna be the 36 is now a 6. Then the y is gonna be a -1, and the z is gonna be a -2. And we couldn't really find that many uses of the Gaussian elimination method in real life, but it is one of the fastest techniques to solve a system of equations. So you could have some system of equations in manufacturing based on something, and it will help. And one example could be to solve the heat equation in some cases. We also have solving linear equations on mesh connected processors, and it is also used in scheduling algorithms. That is it. Thank you.
Okay, good job, you guys. Good job. Couple of comments here. Good job. Particularly well explained the couple of problems at the end. Just a couple of comments. One is that the reason why matrix operations exist and methods like the Gauss-Jordan method exist, and the others that the next two teams are going to talk about, is very simple. If I give you guys a mathematical problem like the system of equations that I gave you, you don't necessarily have to use the Gauss-Jordan method to solve it. Like any of the problems we've seen in class up to this point, you start solving it according to your mental processes. Okay. And you can take 20 steps to do it, or you can take 5 steps to do it. And maybe Ana, Joel, Marco, and Miguel, each of you may do it with a different approach and with different steps, but you get to the result. That's the way the human mind works. Now, how do you implement that in a computer with logic? Okay. So there's only one thing I disagree with your presentation. There's a slide where you say there really is, I'm paraphrasing, there isn't any systematic or particular steps with the Gauss-Jordan method. Actually, there is. Anna, you went through them. There are a series of steps you do with the Gauss-Jordan method. And those steps are systematic, okay? Those steps are systematic. And if they're systematic, I can program them and I can implement them in a computer. And what's the application? Well, if I can have a computer solve a linear system of equations, that linear system of equations can represent a bunch of things. And you mentioned the Adobe and other stuff that have to do with graphics. Computer graphics, a lot of them are matrix based. So the reason we have these methods is precisely so we can implement them in a computer. Miguel, you wanted to say something, and then Marco, and then we'll jump over to the other team.
Yeah, I raised my hand when you said about the different methods that there are. Actually, in the references, the last video, I saw a video of a teacher that was teaching in a international engineering school. He explained really well how you can actually do this also finding the variables using algebra. Just finding one variable, like in the linear system.
You can solve them and substitute, and then etc. You can do
you can substitute them a lot. And then he has a thing called a freedom variable. It's really interesting. It's only like 20 minutes long, and it was worth the while.
And it's good that you guys included it in the reference, and you nailed it there in what you were commenting, Miguel, because we can do it that way. Now, imagine you need to program that.
Yeah, that would take a lot.
Program right now. You need to program. How can I do a systematic method that doesn't depend on doing algebra or anything like that? And actually, you guys are going to take a course in a couple of semesters. It's called numerical methods. That course is actually using these methods to program or to do a program for a computer to solve them. Marco, go ahead.
Oh yes. When we're talking about the programming and all that stuff, on the research, there was a piece of information that caught my eye. It was about how IT companies use matrices to collect user information or perform search queries and all of that stuff.
Mhm.
And it's all through a program using a
Yeah,
matrix.
it's all through computing, and the matrices are gonna, in the end, they're gonna, right now in the examples you gave, there's certain numbers, but the matrices are gonna store data in the end. So that's why the matrix is called the matrix. The movies, they're kind of relating all that to the computer stuff. Well done. I'm sorry, well done, you guys. Let's go with our next house, which is House Pi Waves. Please, you guys have the floor. Go ahead. Give me one moment, please. I need to answer a phone call quickly. One moment. Okay, sorry about that, you guys. Okay, let's continue. Go ahead.
Well, we are team of highways, then we will explain determinants and methods for solving equation systems and the inverse matrix. Actually, I want to tell you that my Wi-Fi is not working and I'm with Datos with the phone, but I think it's okay. Okay, first of all, determinant. As an industrial engineer, as an engineer, optimizing business is basically our main objective. And for this, you can use a lot of tools, and one of those tools are the determinants. And what is a determinant, you may ask? Well, the determinant is a result of a series of operations. Depending on the result, we can know a lot of things because the determinant tells us whether we are dealing with a singular or non-singular system of equations. Therefore, if the result of the determinant is 0, we'll be faced with a singular matrix. And if the opposite happens, that means the determinant is a non-zero digit, letting us know it's a non-singular matrix. Now, when we talk about determinants, we must include their theorems, which are two. Theorem 1, if A and B are both in n times n matrices, then determinant A, determinant B, determinant A times determinant B equal determinant A times B. And theorem 2 is that a square matrix is invertible if and only if determinant is non-zero.
Okay, here we have a determinant properties. There are 6 properties, or I think there are more, but I think I put a 10 on the PDF, but I didn't know how to explain those. I think those were like too advanced, and I found like a video that explained the 6 properties. And the first one is that the value of a determinant is unaltered when the rows and columns are interchanged. So as you can see in the first one, if delta equals A1, A2, A3, and then delta inwards equals like you switch the rows and you put it into columns, then delta is equal to delta inwards. If any 2 rows or columns of a determinant are interchanged, the value of the determinant is changed in its sign. So if you change the position of the rows, the determinant only will change the sign, like the sign flips. So delta is equal to negative delta 1. The third one, if any 2 rows or columns of a determinant are identical, the value of the determinant is 0. As you can see, the first and second row are equal. So therefore, the determinant will be equal to 0. Then number 4, if each element of a row or column of a determinant is multiplied by any number that it's not equal to 0, then the value of the determinant is multiplied by the same number, k. So delta equals A1, A2, A3, B1, B2, B3, C1, C2, C3. Then delta 1, k times A1, k times A2, k times, and like you keep following. Then delta 1, it's equal to k times delta. So the determinant we have, the answer for the determinant in delta will be the same in delta 1, but it will be multiplied times the number we're multiplying inside the numbers, like the k1 and k2. And number 5, each element of a row or column is expressed as the sum of 2 elements, then the determinant can be expressed as the sum of 2 determinants of the same order. Here you can see that there is the A1 plus D1 and A2, and like following that, you can like split them, and the answer of those 2 determinants will be the same as both like together. And in the 6th one, it says that each element of a row or column of a determinant is multiplied by a constant number not equal to 0, and then added or subtracted from the corresponding elements of any other row or column then the value of the determinant is unaltered. Here we start in the left upper corner where it says like A1, A2, A3, B1, and like you keep following with that, like equals A1 plus K A2, then the A2, A3, B1 plus K times B2. Then the example says that if delta 1, if delta is equal to that one, then delta 1 equals to the other like the other matrix. The solution will be that delta 1 it's equal to A1 plus K A2, then A2, A3, and if we jump to the other step, we split them, and we have A1, A2, A3, and in the other side, we have the K times A2 plus, no, K A2, then A2, A3. And if we can like see as the property number 5 in the one we saw before this one, the delta 1 it's equal to A1, A2, A3, and B2, B1, B2, B3, C1, C2, C3 plus K, the number, and then A1, A2, A2, A3. And as the property number 4, as a column, 1 and 2 of the second determinants are the same as the properties 3 sets says, the value of the determinant becomes 0. So therefore, delta 1 it's equal to just the matrix that we have in the left, because the one in the right it's multiply the number of the right, it's multiplied by the 0, so it will stay the same. So therefore, delta it's equal to delta 1.
Okay, so we got the inverse matrix of a square matrix. The inverse of a square matrix A, which is denoted by A1, is the matrix, so the product of A and A1 is the identity matrix. The identity matrix that results will be the same size as the matrix A. And then there's a lot of similarities there between real numbers and matrices. The multiplicative inverse of a square matrix is called its inverse matrix. In other words, for every square matrix A, which is non-singular, there exists an inverse matrix with the property that, as you can see, we have that property where the E is the identity matrix of the appropriate size. Okay, so yeah, I don't know if you can see that very clear. So we got the inverse matrix method for solving linear equation systems. To solving a system of linear equations using the inverse of a matrix requires a definition of two matrices. X is a matrix representing the variables of the system, and B is a matrix representing the constants. Using matrix multiplication, we may define system equations with the same number of equations as variables, as AX equals B. To solve a system of linear equation using an inverse matrix, let A be the coefficient matrix, let X be the variables matrix, and let B be the constant matrix. Thus, we want to solve a system AX equals B. For example, look at the following systems, and then we got some examples of some equations. Yeah.
So moving on with the examples, we have an example of a 2x2 determinant, and with with the steps. So first we have the 2x2 determinant, and in this case we have that the determinant is right here in the middle of the page of the slide. It says calculate the determinant of the following matrix. The matrix is C is equal to 8, 6, 3, and 4. So to demonstrate the determinant, we use these bars. So we now are saying that the C, we're getting the determinant of the matrix C. And to get the determinant, we multiply diagonally. So 8 times 4 minus 6 times 3 and will be 32 minus 18, and the determinant of C would be 14. So in the example number 2, we have an example of the inverse of a square matrix. So we have that in a matrix. Let me move this. If we have the following matrix, 7, minus 2, 3, and 5, its inverse can be found by following these steps. So the first step will be switching the element of the main diagonal, which is the first number in the top left and the number of the bottom right. So we flip the 7 and the 5. Now the 5 is above the 3 and the 7 is below the minus 2. Now we take the opposite of the other two numbers, the ones we didn't flip. So we have minus 2 and 3, and its opposite will be multiply them by minus 1. So minus 2 times minus 1 is 2, and 3 times minus 1 is minus 3. So now that we have the opposite of these numbers, we can now really do the calculations to get the inverse of this matrix. So we have to find the determinant, which we already saw how to get it in this slide, that is multiplying diagonally. So in this case, we multiply 7 times 5 minus 3 times 2. So it would be 35 plus 6, and this will be equal to 41. So the determinant is equal to 41. And we have now that the inverse of the first matrix we had, that was 7 minus 2, 3, and 5, is now 5 over 41, 2 over 41, minus 3 over 41, and 7 over 41. This can also be represented as having only the numbers without the denominator, and having 1 over 41 at the outside of the brackets. So it is multiplying everything, because when we multiply a matrix, we multiply by every element of the matrix. In the example number 3, we have how to solve a linear equation of systems. How to solve a linear equation system using the inverse of the matrix. Our system we have is 3x plus 8y is equal to 5, and 4x plus 11y is equal to 7. So the step number 1 is to write the systems in terms of a coefficient matrix, a variable matrix, and a constant matrix. As my partner Jesus said, we have the coefficient. Because we have 3x, we put the 3. We have 8y, we put the 8. Then we have in the other equation, we have 4x, we put the 4, and 11y, we put the 11. And we have our first matrix, which is the coefficient matrix. The variable matrix is just the variables we have. We have x and y, and the constant matrix is our results of each equation, which is 5 and 7. So we represent this by A times X is equal to B, is a property of these matrices that if we multiply the matrix, the coefficient matrix times the variable matrix, we will get the original system of equations, and B is the result. So to get a result, we multiply everything, both sides of the equal sign, by the inverse matrix. And we previously saw how we get that, the inverse matrix. And it is 11 minus 8 minus 4 and 3. So we're gonna multiply that by the original matrix. So this on the first element of this equation is the inverse matrix, and the first element of the
right-hand side of the equal is also the inverse matrix. Here on the right side of the slide, we have how to multiply matrices, but the previous team already showed us how to do it, so I'm not going to go over that. So after all the multiplications, we got that x is equal to -1 and y is equal to 1. And this was all done by just multiplying the matrices by the inverse matrix. Now the applications. First, the applications of the determinant in real life. So in real life, as we saw, we can solve linear equations quickly when there are more than 2 variables. We don't have an example for this in this section of the application because we saw it on the presentation before. You can also use the determinant to calculate the volume of the parallelepiped, which is this three-dimensional shape that is formed by 6 parallelograms. And you can use the determinant to calculate its volume. Then you can also use the determinant to calculate the area of a triangle. This might not be very useful, but because we all know the formula of the triangle, but this is if you don't have the height of the triangle. So it can be useful if you don't have this data of the height. And I also read that the determinant in real life, they aren't as used because it is really like complex and it is really expensive to program them because there are other methods that are like easier for computers to follow. So determinants aren't used as much in the real world. They are just, as they work with very exact numbers, in real life we don't always have real numbers, the exact measurements. So yes. Now the applications of the inverse matrix. This has quite a few applications. So one of them is to use them to solve the system of linear equations, as we saw. The other one is in linear equations, some error correcting codes, linear differential equations, and linear recurrence sequence all use the concept of the inverse matrix. So all of these use the inverse matrix. Also, inverse matrices are frequently used to encrypt message codes. So to send when they send like encrypted messages in war, so the enemy doesn't catch them. The number 4 is that engineers and physicists develop models of physical structures and execute the precise calculation required to operate complicated machinery using this inverse matrix. And finally in this presentation, because they are more applications, in physics, the inverse matrix is used to explore electrical circuits, quantum mechanics, and optics. So this is an example of an inverse matrix used to code messages. This is called cryptography, if I'm not wrong. So they have 2 matrices, and you get the inverse of the matrix that is here, and somehow you get the message I surrender. The original message was 63, 36, and all these numbers, and actually the encrypted message says I surrender. So that's, I think, pretty cool that they use inverse matrices to do this. And that's all for us.
Okay, thank you guys. Thank you. Good job. Okay, let's stop sharing the screen. So yes, we're continuing to see these, again, these systematic methods to be able to represent, in this case, systems of equations that again, these are going to represent behaviors and phenomenons in real life. And yes, one of the earlier applications of inverse matrices had to do with these encryption protocols to be able to transmit messages. Basically, there was a coded matrix, which was sort of like the key. You calculated the inverse to the data you were receiving, and that would give you the coded message. So those are some of the earlier applications. And again, these methods are systematic methods that can be implemented through programming. Okay, good job, you guys. Let's go with our last house, is the house jokers. Please, you guys have the floor.
Sure.
Yes, please.
When I was looking for the theorems about the theorems, I found the theorems, and like behind those theorems, it came with some proofs, like proof from theorem 1 and proof from theorem 2, but I wasn't sure if to put them in the presentation or not. I don't know if it was necessary to put them.
That's fine. Just those are other variations, Luis. That's fine. Okay. Okay, good. So let's start off with last but definitely not least, house jokers. Please go ahead.
Okay, so hello, we're the last team, House Jokers, and today we're going to present methods for solving equation systems, Cramer's rules, and software tools for math engineering. Well, the team is made by Iván Aceves, Luis Espinosa, Jaime Valenzuela, and myself, Andres Doname. So we're going to be seeing the Cramer's rule, which contains his bio, his rule, and some examples and explanations.
We're going to start with Kramer bio. His name was Gabriel Kramer, and he was born on July 31 in 1704 in Geneva, Switzerland. He passed away on January 4 in 1752. In a summary, he's best known for his formula for solving simultaneous equations. He was extremely smart. When he was only 18 years old, he was awarded a doctorate thanks to submitting his thesis about the theory of sound, and only 2 years after that he was competing for the chair of philosophy at the Academy de Calvin in Geneva. Through his life, Kramer had many achievements and won several prizes for his work. Overall, he was a very hard worker and developed a lot of advancements in math and calculus, such as Kramer paradox, the Catalan-Kramer problem, and his role in his most important work was the reading of Introduction to Analysis.
Okay, so let's start off with the Cramer's rule. So basically, the way this works is that when you're giving any, well, in this case, we're going to be using a 3x3 linear equation, which basically, when you have 3 equations, and those 3 equations have 3 variables, this can be x, y, and z. So Cramer's rules helps us solve these equation systems in a very easy way, without having to solve the whole equation, which well, is a very long and hard procedure. And basically, we're going to be using matrices, which, well, we have been seeing throughout the whole presentations. And we're going to start off with, in the left-hand side, we're going to have the variables and their coefficients. We're going to be using those coefficients in a matrix, and then we're going to be using the right-hand side, which has the answers of each equation, and we're going to be using another matrix. And then, well, we're going to be seeing in the next slide how all of this works, but well, if you want to find the answer of the variable, basically we're going to be using any variable, in this case, well, to explain it, beta, and we have to evaluate the determinant coefficient the determinant of beta divided by the determinant. So now, well, here is the example. So here we have the system, which is 2x plus y plus c equals 3, x minus y minus c equals 0, and x plus 2y plus c equals 0. So we can use this table to organize all of our information. So for example, here are all of our systems, and here in blue is highlighted the coefficient of each variable. So once we have the matrix, you can see that we have the 2, the 1s, the minus 1s, the 1, the 2, the 1. And we also have another column which has the answers, which is basically all of the right part of the equals. And now that we have all of these, we can start like using the Kroner's rule, in which we have to replace the values in the answer column in the column of the variable we have to solve. So for example, in dx, we replaced all of the x values with the answer column. So instead of having 2, 1, 1, we have 3, 0, 0. And we do the same for the other variables. In here, the y is 3, 0, 0, and here the c is 3, 0, 0. And then, well, we start evaluating all of the determinants, which we already saw in the other presentations. And in here we have 3, in here we have another 3, in here we have -6, and in here we have 9. And well, lastly, we have to use the formula that I said before. The value of the variable is the determinant of beta divided by the determinant. And well, first we have of x, which is 3 divided by 3 equals 1. Then we have of y, -6 divided by 3 equals -2. And lastly, 9 divided by 3 equals 3. So, well, like my classmates already explained, determinants are like not very, don't have a lot of applications. Mainly we can use them for these types of systems. And well, personally, I think it's very curious how we can use something like this, and it makes the procedure very easy. But for example, we cannot use this rule in any case if the determinant that is made of the answer column gives you, wait, no, not the answer column, the determinant, the base determinant gives you a result of 0. You cannot use the Cramer's rule because well, you cannot divide something by 0. So this means that either it has other like more each variable has more than one result, or simply you have to use another method. So while it is a very like fast method, it doesn't work in all of the cases. So it's always important to get to know other methods. But well, yeah, this method can help us a lot if the determinant isn't going to be 0, and we have to like make it quick in like physics test, math test, and chemistry test, etc.
Sorry. Right now, to tell you about the software tools for math engineering. There are like two basic that we're going to present. That is MathWorks, that is the company that have like everything. MATLAB, that is a software overview. So we're going to see some characteristics about it and how it works. And my classmate Ivan is going to show some examples of how it works in MATLAB. Okay, first of all, what is MATLAB? MathWorks, sorry, is a company that specializes in developing mathematical computing software all around the world. Scientists and also engineers use this computing software in order to accelerate development, discovery, and innovation. Their main goal is to change the world by using their innovative software by providing the ultimate computing environment for technical competition. So basically, they develop softwares in order to make easier the work for engineers and some scientists. like this MATLAB that we're going to present is a software that makes like everything easier for them. Could you change the slide, please? In the business, in the business side of things, they aim to become the leading developer and supplier of technical computing software. Most of their business activities revolve around quality, innovation, and competitive awareness with a focus on outstanding customer service to their customers. As I mentioned before, this company tries to be like the leader, the best one of all the companies that exist. They try to make easier the life of everyone. And well, in order to have like a preference of their customers, they obviously need to have a lot of quality. They need to be very aware of what their customers want and what their customers need. So that is why they have a good customer service. And also, well, like every company, they try always to improve and make it better. Here are some statistics and numbers that the MathWorks employs all are over like 3,500 people. 30% are from the United States. As I mentioned, they try to be the leader on the world, not only in the United States. So this is like an interesting fact. MathWorks has customers in over 180 countries with 2 million users of MATLAB worldwide. This is just like another stat about and how they are like almost a leader or the leader of these companies. Here's another part of this overview. MathWorks offers two important softwares that were the ones that I mentioned at the beginning of this presentation, that say that MATLAB and Simulink. These two softwares are used through different industries, such as the automotive, electronic communication, and the industrial as fundamental for R&D, research and development. So basically, that's it. They try to do easier the life of everything and the work from some engineers and scientists.
Okay, so what is MATLAB? MATLAB consists of a high-performing language. It stands for Matrix Laboratory. It is used for technical computing, programming, and visualization of all of this is inside an easy-to-use technical program where mathematical problems or solutions are expressed in a familiar mathematical notation. Some of the uses of the software are computation of mathematical problems, algorithm development, prototyping, simulation, and modeling, data analysis, engineering graphics, and application development. Okay, so its main characteristics is that it is a high-level language. It has interactive graphics. It has data access and processing. It has an interactive environment, and MATLAB can interface with different languages. And the advantages of using MATLAB is that, well, it has an easy-to-use interface, a large inbuilt of database algorithms, debugging of codes, and easy symbolic manipulation. Okay, now we're gonna stop sharing screen and we're gonna go to MATLAB. All right, okay, so here we're looking at MATLAB and the whole program. So let's get started. So this right here, what I have selected is called the editor. Now the editor is where you write your code or what you're trying to do. And over to the right, we have the workspace. The workspace allows you to visualize in an easier fashion what you're actually doing. So, and down here we have the command window, which is where your program gets run and you can see the output of it. Hold on, I think I have something wrong here. No, everything's fine. Okay, so let's get started. So how do we define a matrix in MATLAB? Well, the first thing we have to do is give our matrix a name. So for example, here we have two matrices. We have A and B. So in order to tell our program that this is a matrix, we have to put everything in between square brackets. So as you can see at the start of it, I have a square bracket, and at the end of it, I have 1, 2. And I have a semicolon at the end. What the semicolon at the end does is that it suppresses the line of code. meaning that it will not get projected when I run the program. So if, for example, if I erase this, I will get projected what I'm trying to do. Even if I put the semicolon back on, I won't get it right here. So this is something I was testing out earlier. Just ignore this. And so let's continue defining the matrix. So the way you do this is you write down the data that you're trying to put inside the matrix. So for example, we have these numbers. We have 2, 4, and 6. So this is one row of our matrix, and each number is separated by a space, which indicates that it is a different number. And so then, in order for us to jump a space or to press enter, we must write down a semicolon like this, and then we can write the next set of numbers, and it must be the same size as the numbers before. So it has to have 3 columns. So for this to be easier to understand, we can go over to our workspace actually, and we can take a look of what I'm talking about. So for example, this is the matrix that will be generated through the line of code. So this is easier to visualize. And this is another one. This is B. This is a B matrix. This is the name of it. So this one has 2 sets of columns for each row, and it has a total of 3 rows. And it is exactly the same as this, just in a different size. So if we go over to B, we can see that this is the way it would be represented within our workspace. Okay, so now how do we multiply and do division in between 2 matrices? Well, for this example, we're gonna calculate distance. And we know that distance is the multiplication of time and velocity. And so here we have 2 already predefined matrices, which is time and velocity. And we can see that this is a 1 by 5 matrix, or a 1 row and 5 column matrix. So in order to tell our program that we want to do a multiplication for each of the elements, meaning that I want to multiply 0.5 times 15, in order to tell my program to do that, I have to write down the following symbols. I have to write down a dot and a star. This dot and a star means an element-wise multiplication, meaning that I will multiply the first element of each matrix by each one of the other matrix. So if we were to run this, so let me just remove the semicolons at the end so that I can actually show this, it will look like this. So we can see that the multiplication of time and velocity will give us the distance, which is 0.5. So you can already start to see how this would be very useful in engineering for solving different problems and doing automatic stuff. Okay, so let's say that you only have the distance and the time and you want the velocity. Well, we know that the velocity is distance over time. So in order to do that, all we have to do is define again that we're going to do an element-wise operation, and then write down a slash for division. So if we were to run this, we can see that we will get the velocity from the previously defined matrices. So let me just close this again. And what about a single element extraction of a matrix? In this case, this is a lot like playing Battleship. So for example, let's go back to the matrices we had to start. Let's say that we want to take number 4 and we want to multiply it by number 11. So what we need to do is see where number 4 is located. So number 4 is located in x1, y2. So we would write it down in our code as 1, comma 2. It's exactly the same as like a graphical function like we've seen before. So 11 in B is in 1, 1. So we just write down 1, 1 with a comma. And this, if we run this, we can see that the single elements will be extracted and they will be multiplied, which equals 44. Now, what if we wanted to do that for an entire row or column? Okay, so let's get started with columns. So for columns, you first have to define what column you're trying to find. So in this case, we're gonna do it inside the A matrix. So we're trying to find column number 2, and we have to write it down within the Y values. So this means that it will only consider column number 2. So if we go back over here, we can see that this would be, no, this is B, this is column number 2. So it has to, we want to only take out these 2 values. And so how do we tell that to our program? We have to use this 2 dots right here, which is a colon, I think it's called. And so this means all the possible values of X. So if we were to run this, we can see that we would extract only the second column of the first matrix, or matrix A. So let me just suppress this again. And what about a row? For the row, you do the exact same thing. You just define what row you're trying to find. For example, we're trying to get this row right here. So we would define that we want only x1 and all the possible values of y. So 1, all the possible values of y. And if we run this, we can see that, well, we get that row. And what if I wanted to get a matrix from another matrix? Well, if we go over to matrix B, let's say that I want to make another matrix from these 4 numbers right here. What I would need to do is tell my program the following. So this is the set of values of x, and this is the set of values of y. This is the first or the start of your values of y, and this is the end of your values of x. I mean, the values of x, and this is the end of your values of x. This 3 right here. So since I want to take only these numbers, I would only take from 2 to 3. And how do I tell my program that I also want to get these other 2 numbers? Well, you have to include that I want from column 1, from column 2. So you write down 1 to 2. So when we do this, we can see that we get another matrix from another matrix. And I named it bottom middle submatrix so that you guys can understand better. And so this was just a brief introduction and some examples of the fundamentals of matrices and how we can use them in engineering and this program. So if we can go back to the presentation right now. Okay, so some examples and applications of this are plotting graphs, scientific studies, and they are by far the best representation methods for plotting surveys. And they are also commonly used in computer graphics and image processing to create effects like reflections or even ripping water, as the teacher already mentioned before. Okay, so that was our presentation. Thank you very much for your attention.
Hey guys, great job, great job, and particularly
Great job in the explanations. I really liked and appreciated that you actually presented an example in MATLAB. That was really good. You're going to be using MATLAB a lot in numerical methods. That's that course that I mentioned where basically you're going to be using these matrices and implementing them in the software. And so MATLAB is one of the softwares that you're going to be using. And it's a very powerful software that's used in industry to do many different types of applications that have to do with math processing. So good job, you guys. Good job with the presentations.